Hi, and welcome to Dr. V's AP Chemistry webcast. Today, we're talking about the light equations. You really need to know quite a bit about electromagnetic radiation in order to be successful in AP Chem. And I wanted to give a special shout out to John and Henry, who helped me prepare this webcast and all the slides and everything. And Henry's here to help me talk to you about the light equations. So, here's what we'd like to accomplish in this webcast. We need to review the light equations and their variables, some of the properties of electromagnetic radiation, and we'll go through and do a sample problem. All right. Again, these are skills that are going to show up. You need to know these relationships, and you need to be able to do the math conceptually and quantitatively. So let's start by talking about the speed of light. We're going to focus on the speed of light in a vacuum. The speed of light is given the symbol c. We're going to treat it as a constant. So for all the problems that we do, we're just going to use the speed of light in a vacuum. And we're going to assume that all electromagnetic radiation is traveling at the same speed for the problems that we're doing. It has a value of 2.998 times 10 to the 8th meters per second.
For those of you who are unfortunately still stuck in the imperial system, that's about 671 million miles per hour.
That's really fast.
Pretty fast.
Pretty fast. It's not a constant you have to really worry about memorizing. It is on your reference sheets for AP Chem, which you have throughout the entire exam. On the other hand, what I find is my students use the value so often that they end up remembering it. The other constant that I wanted to introduce was Planck's constant, which is given the symbol H. And it's got a value of 6.626 times 10 to the minus 34 joules times seconds. Now, for our purposes, we're really going to use it as a proportionality constant. It actually has a lot of other applications, but right now we're focused on using it to help find energy of photons and using it in these equations that we're going to be developing as we go through the webcast.
And again, don't feel any need to memorize this. This one's definitely on your formula sheet.
Oh, yeah. It's not an easy number to remember.
No.
Okay. One of the important characteristics that we use to describe electromagnetic radiation is the wavelength, which is given the symbol lambda, the lowercase Greek letter lambda, not the uppercase lambda, that's a different thing. And wavelength is really that distance from peak to peak or from trough to trough. We've got it labeled 3 different ways on this particular diagram. And you should be able to identify that from a picture of a wave. Right, crest to crest or trough to trough is the easiest way to do that.
And this is, of course, a distance measurement, as you can see on the diagram. So for most purposes, this will be written as in nanometers, but for problems, you're going to be able to convert that to whichever unit makes the most sense.
Right. Often we have to convert it to meters if it's
right.
measured in something else, because our speed of light is in meters per second. And we want to put that all together. The other important parameter that we use when we're talking about electromagnetic radiation is frequency, all right, which is given the lowercase Greek letter nu. It's not a V. I know everyone wants to call it V, but it's really nu, and you're going to sound much more informed if you say nu instead of V. It's cycles per second or wave fronts per second. It's basically cycles per time. Usually we're doing it in seconds as our time unit. You might see it written as hertz or inverse seconds. These are all very common units for frequency. One of the important relationships between wavelength and frequency is that they're inversely related, and you do want to really know this conceptually. We'll talk about the math of it in a minute, but knowing that relationship is kind of important. Let's go on and look at some illustrations that will help us just grasp that idea. All right. So if we have waves, electromagnetic radiation, and we're assuming they're all traveling at the same speed, well, we have 5 different waves here. All right. If we look at the red one, clearly it's got the longest distance from peak to peak. It's got the longest wavelength. But that means in that amount of time, only a few wave fronts are going to hit you. Whereas if we look at the purple light, the wavelength is much, much shorter, but a lot more waves are going to hit you in the same amount of time. So we can see that inverse relationship. When the wavelength is long, the frequency is small, and vice versa. So that's an important relationship to know. Now, there's also a relationship between the frequency of the light and the energy of the light. Right? If more wave fronts are hitting you, more energy is going to be transferred to you. So energy and frequency are directly related. So your purple light is going to have a much higher energy than your red light.
For instance, that's why so many sunscreens try to block out UV light from the sun, because that has a high frequency and it's considered to be more damaging.
Right. It's got a lot more energy than your infrared.
Right.
All right. So there are some key equations that we use when we're talking about electromagnetic radiation. And we talked about them conceptually. Let's put the math together. The first is that we know that wavelength and frequency are inversely related. When you multiply them together for electromagnetic radiation traveling through a vacuum, it's equal to the speed of light. So C equals lambda nu. This is a really useful equation. You really want to know this one. Know it conceptually, and then we'll talk about doing the math. Another important relationship, we talked about how energy and frequency are directly related. All right, so we need the proportionality constant. That's where the Planck's constant comes in. But we can clearly see that as your frequency increases, the energy increases as well. We can put these guys together, and when we do, we get the relationship E equals hc over lambda. This is useful because it does show the relationship between wavelength and energy. As the wavelength increases, the energy goes down. So energy and wavelength are inversely related, and that's, again, a useful relationship to know. So you don't really have to know this third equation separately. You can just derive it on the fly when you need it, but it's really helpful. My tip always when you're doing any of these problems, algebraically manipulate the equation you need to get the variable you're trying to solve for before you go put any numbers in. My students know that I say this all the time. Some of them listen. Some of them don't. It kind of depends. But it really is a good strategy. All right. Again, general problem solving strategies, list your variables out, think about your units, think about your sig figs, make sure your answer makes sense. These are all things that you have to pay attention to. But these are the key equations. And if you know these, you should be able to do pretty much any problem you're going to encounter in AP Chem. All right, so here's a nice problem. Photosynthesis uses 660 nanometer light with a wavelength of 660 nanometers to convert carbon dioxide and water into glucose and oxygen. So the first thing we're asked to do is calculate the frequency of the light in inverse seconds or hertz. All right, so things to keep in mind. Our wavelength was measured in nanometers. That's a very common unit for electromagnetic radiation in the visible spectrum. They're usually in the nanometer range, but we are using the speed of light in meters per second. So really we need to make sure all our units match. So converting nanometers to meters is really helpful.
If you really wanted to, you could convert the speed of light to nanometers per second, but that would be an unpleasant conversion.
It's really not fun.
Much easier to do it the other way.
I do recommend that you memorize the conversion. 1 nanometer is 10 to the minus 9th meters. If you prefer to put this as, there are 10 to the 9th nanometers in 1 meter, it's all the same in the end, but you do have to make sure you can do those conversions, but this is not a conversion factor that's given to you on the formula sheet. You really need to know it because it's going to show up. The other thing to keep in mind is that we are solving for frequency. We have a wavelength, so we know that C equals lambda nu, and we can substitute and evaluate. But first, we want to rearrange our equation. Since we're solving for nu, our frequency, all right, we can go ahead and do that. So nu equals C over lambda, and then we can substitute in. We know C, the speed of light, that was given to us. It's on your reference sheet. Hopefully you wrote it down when we gave it to you a few slides back. We just found the wavelength. We have to convert that into meters. So we can go ahead and substitute those values in. I always like to put my units in and make sure that they cancel. The meters are going to cancel. I'm going to be left with 1 over seconds, which makes sense because I'm solving for a frequency. And when we substitute that in, we get a frequency of 4.39 times 10 to the 13th per second, or cycles per second. We do want to pay attention to sig figs. Our wavelength had 3 sig figs, so our answer should have 3 sig figs. We have plenty of precision for the speed of light, so that's not going to limit our answer at all. All right. Now there's a second part to this problem. What's the energy in joules of a single photon of this light? All right. We had already, started some work on this problem, so we already had the frequency, so we can actually use that. Again, we know that E equals h nu, and so we can just substitute that in. So again, we have to go back and pull out our value for Planck's constant, substitute that in, and we get an energy of 2.91 times 10 to the minus 20th joules, which seems really good.
And on the AP exam, there's a good chance they'll ask you for energy per mole. So you can just multiply by Avogadro's number there.
So this is a single photon of light, one little packet, right? Because light can act as a wave or it can act as a particle. So this is a single photon, so that comes up. The other thing I want to remind you is make sure you show your setup and your work when you're doing these problems. Very much an expectation that it's going to be there, because if you don't have the supporting work and there's something wrong with your answer, we don't know what happened. So it's just good advice for yourself to show all that work. If you feel you need extra practice with wavelength, energy, and frequency problems, the online homework site out of Cal State University at Domingo Hills has a interactive practice site, which will give you instant feedback on whether you've done it correctly, and you can do a lot of extra problems there, which are very helpful. Great, well, we'll stop here. We'll talk another time.